Hi, this is Susan again, and in this demo I'm going to continue following the recoding demo that I did previously. So now that you've recoded items as needed, if this were your actual research project, you next might want to create aggregate scores on the items, either by summing or taking means of the item responses. Now keep in mind that in a real study, you would probably already have run internal consistency reliability estimation and possibly exploratory factor analysis prior to creating total scores, and we'll cover those two procedures in Unit 4. So I'm going to show you 4 different approaches to computing sum scores so that you can see what happens when you have missing data. I've already pasted the syntax so you won't have to watch me type, and I'll assume you've watched the video links I provided that showed how to use the compute procedure. So I've got these 4 sums that I'm creating, sum 1, sum 2, sum 3, and sum 4. And just as a note, if you haven't already pasted syntax from the compute procedure, when you use the pull-down menu for the compute procedure, everything that you type in the numeric expression box is going to show up to the right side of the equals when you paste the syntax. So I had typed in the v4 underscore r plus v9, etc. in the numeric expression or the sum function and so forth, and that's what got pasted in. So 2 of these methods, sum1 and sum3, are going to impose list-wise deletion of missing data, whereas the second sum procedure is going to return or produce sums as long as there's at least one variable with a valid value. And then the fourth procedure, the fourth sum, requires respondents to have valid values on 4 of the 5 items, which also means this approach allows them to have up to 1 missing value across the 5 items. And the way we specify that is after the sum, and it may be difficult to see on the screen, there's a 0.4. So that number 4 says that 4 of as many items as there are in the parentheses have to be valid in order for a respondent to receive a sum. And note that the number following the dot can be changed depending on the number of variables or the number of items. So for example, if I had a 20 item scale and I was adding the items, I would maybe designate 0.18 or 0.19 to indicate that I'd give a sum as long as we had 18 or 19 valid values. So now I'm going to highlight and run these 4 compute statements. And notice also I did add comment lines. I'm going to hit Control R. And if I don't get an error message, it's kind of no news is good news. It probably means it ran correctly. I can also check in the data file itself, and I should see those at the end when I create new variables, and there they are. You can see there are some blanks for missing data, which is why we have an issue. And I'm going to run frequencies on those 4 variables. So I'll go to descriptive statistics, frequencies, and any new variables we create always go to the bottom of the list. Highlight sum 1 through sum 4. And I'm going to also ask for charts and histograms because we're going to look at a histogram here in a minute, and click OK. And for right now, I just want to point out the valid versus missing values. And as you can see, for the 2 procedures, which are sum 1 and sum 3, that require list-wise deletion of missing data, we've lost 32 respondents. For the procedure that allowed up to 1 missing data value, we got back 24 of those, or in other words, we only lost 8. And then for the procedure that allowed us to receive a sum, if there's at least, if even 1 valid value, we lost 1 person. That means that there was 1 respondent who didn't answer any of the 5 items. So I also want to look at a list, and this is just another way of seeing what happens when we create these variables. The list variables is a command that we only can get through syntax. We'll look at that actually in our next unit on syntax, but I'm going to highlight it. And it's kind of just a nice handy procedure because I can list, whoops, that went too fast, variables in columns, and we don't need to look at all 300 and something respondents, but one of them I wanted to show was this person only got a sum if we use the unrestricted method of having only one valid response. This person answered questions 4 and 9. They did respond with the strongly agree, so they had the high value, and they were missing the other 3. And then the other one I wanted to point out is right here. This person has a total score of 1, which is actually out of range. And why would I say it's out of range? Well, that's because we would expect that the possible range of total score should be from 5 to 25. So someone who had rated all 5 items with a 1 or strongly disagree should have the lowest possible score of 5. So there are a couple of problems here. So for example, this person who has a 10, and I'm going to scroll back up to the histogram, and I'm going to go here, which is actually a little shortcut. I'll go over to the little menu here. Notice that a score of 10 is on the low end of the distribution, and yet for the 2 items that this respondent completed, she had strongly agreed, and I know it's a she because I have the data and I know their genders. But it would be misleading in terms of this total score that she's actually at the low end of the continuum. So what effect do you think this might have on an analysis such as correlations, t-test, ANOVAs, and so forth if there were a number of cases with this type of data pattern? So it's just something to think about. And we have a couple of issues here. One is that the sums could be misleading when there is item level missing data and list-wise deletion is not imposed when we create the sum scores. On the other hand, the second issue is that we can lose a lot of data if we create our sum scores based on list-wise deletion of missing data. So for example, in this case, we would lose 32 participants if we summed the scores with list-wise deletion required. So how do you reconcile these 2 competing issues? Well, one possible approach that's reasonable when the sum scores are based on a large number of items is to compute a summed score but allow 1 or 2 missing values, such as the 4th method I used above, that was the sum 4, to compute a total score. In this case, I gained back 24 subjects when I use this approach compared with using list-wise deletion. And although the sample size in this example data file is fairly large, in a study where losing 24 subjects could be the difference between having sufficient versus insufficient statistical power, this approach to creating a sum score would be useful. And even though I'm illustrating this approach with a scale that only has 5 items, mainly just for simplicity and being able to show everything on the screen, I wouldn't actually use this approach with such a short scale. So think about why it's not advisable to use this approach when you only have a few items in the scale or only a few variables of other types that you plan to aggregate. So another possible approach to creating aggregate scores is to create mean scores instead of sums. And you basically have the same options for creating mean scores as you did for sum scores, but for purposes of illustration, I'll just talk about 3 of those. One is using list-wise deletion, so you can use the mean function and then impose the same .5, for example. You can also use the unrestricted method with the mean function and create means as long as there's at least 1 valid response. Or you can use the more restricted approach that applies a specific restriction but not list-wise in terms of valid values. And if you haven't already explored the available functions within the compute procedure, you might want to do so. The mean and the sum functions are just a couple of options. So I will walk through one of these just to show you. If I go to transform compute, and we have lots of functions over here. So for example, under statistical functions, you can see mean and sum. There are many others. You've got missing values, you've got random numbers, and just many that we won't have time to cover. So I'm going to create a variable. I'll call it mean, maybe just mean1, just to be simple about this. And I'm going to type mean parentheses. I could click the mean, but in this case, if I want to just allow unrestricted computation of calculation of means, I'll use mean I can click this over and then a comma, and then click this over and then a comma. Personally, I find it easier to type, so I'm going to type it, and then v4 underscore r comma, well, I said it was easier, but then I made a typo here, r, and then v9 underscore r. And then I can paste that syntax, or you can just run it. Let me go back to the syntax file. And then I can highlight this. And then I'm going to run descriptive statistics, and just for our purposes, I will run means and standard deviations. So you can see that we have an N of 395. The minimum value is a 1. A maximum value is a 5. This is the unrestricted, so even if they just had one item, we're still going to have a range from 1 to 5. And it would change if I used the mean 0.5 or 0.4, or use the addition and then divide it by 5 to compute the mean. So for your own research, or for some of you who might be consulting with others on their research, you should consider the relative advantages and disadvantages of the different methods for computing aggregate scores. And this is a topic for discussion in the Unit 2 discussion forum. And that's about all I had for the topic of creating aggregate scores.